Students, in today's lecture, I am going to discuss another type of nuclear reaction which are very important to understand some of the important features of nuclear astrophysics. For example, when I have discussed the salient features of the universe, selected general properties of the universe, if you remember, I have discussed triple alpha reaction, right? The existence of carbon in the universe and what is the role of triple alpha reaction in the formation of carbon 12 nucleus. While dealing this topic, I have said it was a two-step process. Initially, alpha plus alpha gives rise to beryllium 8, then it is reacting with another alpha particle to produce carbon 12. That was happening at a particular excited state of the carbon 12, right, which we call as Hoyle state. So, like this, there are many important reactions which occur only at a specific value of the projectile energy, and we call them as resonant reactions. So, in today's lecture, I am going to focus on the topic resonant reactions, nuclear reactions happening at some resonance energies. Okay. So, before that, let me spend a couple of minutes on the content of previous lectures so that I can maintain the flow. Okay. So, in the recap, please remember I have discussed non-resonant reactions induced by charged particles. Non-resonant induced charged particle reactions, where sigma cross section is smooth function of energy, of projectile, right. And we have seen the concept of gamma peak, which occurs because of the product of e to the power of minus 2 pi eta and e to the power of minus e by kt. Then I have discussed the importance of centroid of the gamma peak E naught, that is most effective energy, and width of the gamma peak, that is delta, and the maximum value corresponding to the centroid of the gamma peak I max. Okay. And what is the dependence of these parameters on Coulomb barrier, and finally the temperature dependence I have discussed. Temperature dependence I have discussed, and I have presented a lot of data which clearly states that the change in the Coulomb barrier dramatically changes the values of centroid of the gamma peak, and it is the range of E naught plus or minus delta by 2 over which the majority of the nuclear reactions take place in stars, and they are the nuclear reactions which are playing important role in the energy production and also in the nucleosynthesis finally. After this, I have discussed an important correction, okay, that is electron screening effect, right. But anyway, when I said two corrections in the reaction rate of non-resonant charged particle induced reactions, please remember they were the dependence of S factor on energy and asymmetryness in the gamma peak, asymmetry of gamma peak. So, these two corrections have to be considered practically. After that, there is one effect called as electron screening effect, which is based on the fact that whatever discussion was done, it was considering that it was considered that the nucleus was bare. There were no electrons surrounding the nucleus. Within the stars also, almost all reactions are taking place without the presence of electrons around the nucleus. But in laboratory, when projectiles react with the target nucleus, these target nuclei are surrounded by nucleus. So, in fact, you have the atoms inside the target material. So, whether the presence of electrons surrounding the nucleus will have any role in the measurement of cross section, and the conclusion we have seen was it is negligible. Except at high stellar density, one can ignore the electron screening factor small f. So, up to this we have discussed in the previous lectures. Now, in today's lecture, as I said, I am going to discuss another type of nuclear reaction, that is resonant reactions. Resonant reactions. So, how we are going to deal this topic? In the same way as I discussed non-resonant reactions. The aim is to write down the expression for reaction rate for resonant reactions. How one can calculate the rate of resonant reactions? Fine. Let us see how these resonant reactions are important and how to calculate how to come up with an analytical expression for reaction rate when resonances are involved. Okay. So, one of the best ways to understand any topic is to start with some questions, right? Like in the previous lecture, I have asked a few questions regarding gamma peak and also the importance of non-resonant reactions. Similarly, I am making an attempt to prepare a list of questions so that we can understand the concept of resonant reactions in a better way. Okay. Is resonant reaction a one-step process like non-resonant reaction, or a two-step process? Right. In one-step process, what is happening, like in non-resonant reaction, the Q value, okay, and the projectile, it is directly going into the, this is a final nucleus, right? This is the final nucleus. For example, take a target nucleus, X is a projectile, and for the sake of convenience, let us consider the rate to capture reaction, say gamma is emitted and B is the final nucleus. So, here several nuclear energy levels are there within the final nucleus. This can happen in any projectile energies, these non-resonant reactions, and this is directly transition to the ground state or the one of the, at any state above the ground state, right? It is basically direct capture. That is why we call it as one-step process. This is a non-resonant reaction. Non-resonant reactions. And how do you expect, the cross section for this direct capture reaction can be expressed as matrix element given by one matrix operator, okay, and A plus X, and finally this is a B, okay, and this is a H gamma, this is the square. So, this is a electromagnetic operator. It is via electromagnetic interaction. It can occur at any projectile energy. Remember, the reactions in which cross section is smooth, cross section has a smooth dependence on the incident projectile energy. We are calling them as non-resonant reactions, and because it is a smooth dependence, it is a one-step process and it can occur at any projectile energies. What about resonant reactions? Is it a one-step process like non-resonant reactions, or is it a two-step process? We will try to understand considering the same radioactive capture reaction. Okay. Can we understand the concept of resonant reactions with the help of the concept of damped oscillator? It is also a physical system, right? There are many physical systems which possess this resonance phenomena. I hope you remember the system of damped oscillator. When external force is applied, it gives the response is maximum only at certain values of the incident force, right? The response is maximum, and those responses we call as eigenvalues. Can we take analogy between this damped oscillator and the nuclear reaction involving resonance energy so that we can get a better idea, and finally we can get expression for the cross section and then the reaction rate we will see. Okay. Now, as I said, one of the common goals of these discussions is the expression for reaction rate when narrow resonances are involved. Now, I am confining to the discussion on narrow resonance. Narrow resonance. The energy level density should be very, very small. Okay. Energy level density should be very small when I say narrow resonance. Some more ways of defining this narrow resonance I will discuss very soon. Okay. Another question, earlier we discussed gamma peak as part of discussion on non-resonant reaction. The product of e to the power of minus 2 pi eta, that is gamma factor, and e to the power of minus e by kt, a factor coming while including the Maxwell-Boltzmann distribution, right? Then we have seen a beautiful gamma peak, almost close to the Gaussian function, right? What about the gamma peak presence in resonant reactions? Whether the resonance region and gamma peak they are same or different? If yes, how? This question we will address in today's lecture. All right. Now, one of the most important question we have to understand in the star's evolution and the role of resonant reaction is whether low level resonances, that means low energy resonances or high energy resonances play important role in the energy production and also in the nucleosynthesis, and finally the stellar evolution. So, the properties of a star, do they depend on low energy resonances or high energy resonances? If yes, why? So, let us see how we can answer all these questions while trying to understand the concept of resonant nuclear reactions happening within the stars. All right. I hope these questions are helpful to you. Now, resonant reactions. Before that, let me give you some examples for non-resonant reactions. Like direct capture, as I have said, A when it reacts with some projectile gives gamma ray and product nucleus B. Okay, this is one type of a direct capture, that is a radiative capture reaction. Then stripping, when incident nucleus takes out few parts of the target nucleus, okay, and then undergoes reaction, this is called as stripping reaction. Okay, so this is also an example for non-resonant reaction. Then pickup reaction. Okay, if some of the incident nucleus, if parts of the incident nucleus are absorbed by the target nucleus, then we call it as a pickup reaction. Okay, and then if there is no change in the mass number, only the exchange of the charge is taking place, then we call them as charging exchange process. And Coulomb excitation, if the incident nucleus excites the target nucleus because of the Coulomb field while traveling near to it, then we call it as a Coulomb excitation and followed by the Coulomb dissociation. So, these are some of the reactions which come under the category of non-resonant reactions. Non-resonant reactions, and they are basically one-step process. Okay. Now, whereas in case of resonant reactions, cross section is not smoothly, it doesn't possess smooth dependence on the energy. It varies suddenly and drastically at a few projectile energies only. Okay, and that too, the energy state of the nucleus is above the Q value. Okay, energy state of the nucleus is above the Q value. Incident projectile energy is not the above Q value, but when incident projectile has some energy, and if the incident projectile energy plus Q value giving rise to some excitation energy, if that matches with the one of the excited states in the nucleus, then we can expect a sudden rise in the cross section of the reaction. Okay, and because cross section is not a smoothly dependent function anymore in resonant reaction, the S factor also strongly varies because of the resonances. Okay. Now, as I said, it occurs only when the incident projectile energy, the projectile energy plus Q value is nothing but one of the excited states of the compound nucleus. This is what we mean by resonant reaction. Okay. Now, this excited state in the nucleus, compound nucleus should be discrete, should be one of the discrete excited states of the compound nucleus. That is the reason it is two-step process. Why it is two-step process? In the first step, the entrance channel goes to the one of the excited states of the nucleus, and in the second step, this excited state decays to the final form. So, in that sense, it is a two-step process. Okay. So, Consider the same radiative capture reaction. How can we envisage as two-step process? As two-step process. In this case, we can say that sigma, which is basically dealing with the gamma emission from the nuclear reaction, is proportional to the two matrix element. If you remember, sigma gamma can be written as two matrix factors, right? Like in the first one, EF final nucleus is formed, okay, and H gamma is there, EX excited state in the compound nucleus is there, and the first matrix element is compound nucleus is formed in the excited state, and formation operator F stands for formation, okay, and A plus X, okay. So, this is the two matrix elements. So, here these two matrix elements represent the probabilities for the two steps to occur. Earlier also, while discussing forward and reverse reaction, I have explained the concept underlying this matrix elements representation. They are connected through some operator. They are connected through some operator decided by the interaction mechanism. Okay. So, this is the formation width, that is partial width, that is probability for this formation to happen, and then this is the decay width. This is the decay width and this is the formation width. So, the cross section of total reaction depends on the cross sections of two individual processes. Number one, the probability for entrance channel to enter into the one of the excited states of the nucleus, compound nucleus, and then the probability for excited state to decay into a specific final state. And we represent these two matrix elements with partial widths, right. So, here this symbol is also called as gamma, okay. So, do not get confused, gamma of this radiation and gamma of this partial width, and this is the formation width and this is the decay width, alright. So, this is the partial width for the formation of the compound state and this is the partial width for the decay of the compound state. It could be particle emission or gamma emission. In this particular case, this partial width for the decay of the compound state can be represented as gamma gamma. Symbols are different, but we use the same name, gamma gamma, okay. So, this is the way we are trying to understand the resonant reaction. So, in this slide I have explained resonant reaction is a two-step process. It can occur only at specific projectile energies, so that the projectile energy plus Q value produces an energy which is just equivalent to one of the excited states of the compound nucleus, alright. So, let us continue the discussion. The properties of this excited state in the compound nucleus, of course, that will decide the magnitude of the cross section. So, when I say properties of this excited states, of course, it comes like lifetime, parity, spin, all those properties comes into picture. Now, here I can assume this formation width and decay width to understand in a better way. So, one approach I am taking the help of, okay. See, what is the maximum cross section a nuclear reaction can attain? It is pi lambda square, pi lambda bar square, okay. Pi lambda bar square is the a cross section, maximum cross section a nuclear reaction can attain, okay. Now, to express in a better way when resonance phenomenon is considered, I am assuming this process as collision between two parameters, okay, collision between two parameters. Number one, the momentum of the projectile, reduced Planck's constant and the wave vector k, which can be represented in terms of reduced Planck's constant by reduced de Broglie wavelength, okay, and the impact parameter So, how can we envisage this? So, this is the axis of the target nucleus, okay, target nucleus along some direction. Now, a projectile is coming, okay, and it is going like this, fine, okay, and assume some distance between the original direction of the target nucleus and the projectile. The separation is nothing but impact parameter. You might have understood the concept of impact parameter when Rutherford alpha scattering experiment was taught to you. Okay. In this particular case, I can assume the shadow of the nucleus seen by the incident projectile as regions, okay, whose area represents the cross section. Okay. And in this collision, if orbital angular momentum is involved, okay, then the product of impact parameter, all right, and the momentum gives you the orbital angular momentum value. So, that is equal to bh bar by lambda bar. Now, in this particular case, the orbital angular momentum also can be expressed as the orbital angular momentum quantum number. Okay. So, in the collision between projectile and target, the orbital angular momentum is involved. That is what we are assuming in this particular case, which is the normal case. Okay. And here B in such case L lambda prime, L lambda prime, the relation between L is equal to BP and L is equal to L H cross, fine. From these expressions we can get the impact parameter in terms of orbital angular momentum like this, L lambda bar. So, L is equal to, they are integers basically, okay, 0, 1, 2, 3, 4 like that. Now, each value of L corresponds to each zone, okay, which is characterized by the value of orbital angular momentum quantum number, all right. And the area of each zone represents maximum possible reaction cross section if all the projectiles are absorbed, all right. And what is the maximum possible reaction cross section for a given value of L? Nothing but the area between successive concentric rings about the nucleus. So, this is how we can relate the orbital angular momentum quantum number and the cross section of the nucleus. Listen to me carefully. Okay. Now, the maximum cross section is nothing but area between the two successive concentric rings, L and L plus 1, corresponding areas. What is the difference? Is nothing but 2L plus 1 into pi lambda bar square. So, this is the maximum possible cross section for a given value of L. If L is equal to 0, 1, 2, 3, 4, accordingly the sigma maximum also will be varying. Remember, this is the maximum. Maximum means beyond which there is no possibility for the cross section to exist. That is the pi lambda bar square. But the cross section, as I said in the resonant reactions, it is changing dramatically at only specific value of the incident energy. And in that particular situation, if orbital angular momentum is involved in the collision, then the value of small l, orbital angular momentum, decides the maximum possible cross section at that particular small l value. I hope you are following me what I am trying to convey. Fine. Now, let us include the spins of the projectiles also and target. In that case, so not only orbital angular momentum, but also involving the spin, one can generalize the 2L plus 1 as statistical factor omega. I mean, this term is nothing new for you, right? While discussing forward and reverse reaction, I have discussed the role of statistical factor 2J plus 1. This is the spin of the compound nucleus, and J1, J2 are the spins of the projectile and target. And if L is equal to 0, of course, it will finally reduces to 2L plus 1 only. Okay. If spin is 0, because J is equal to L plus S, if spin is 0, we can this statistical factor reduces to 2L plus 1 as expected. Okay. For spinless particle, it will reduce to 2L plus 1. Now, we also have to take into account the concept of identical, okay, properties. Then the cross section increases by 2. So, let me express the maximum cross section as this pi lambda bar square and this statistical factor W and the Kronecker symbol taking into account the identicalness of the particles. Now, this is incomplete because we also need to know the concept of the cross section by taking analogy into with some kind of physical systems. Why it is important? That will be clear soon to you. Now let me take the help of a damped oscillator. There are eigenvalues for this damped oscillator. They correspond to the maximum response when external force is given to this damped oscillator. And how do you write down the response of the damped oscillator? Okay, it is basically, you can write like response of damped oscillator as oscillator strength F, and frequency minus frequency at which response is maximum, right? Resonant frequency, this is eigen frequency. This you might be having idea about the damped oscillator, okay? And damping factor delta, okay? So this is how we represent the response of a damped oscillator when external force is involved. Only for certain values the response is maximum, and that is characterized by omega naught eigen frequency. By taking the analogy of damped oscillator, one can write down the resonant phenomenon in the nuclear reaction as, here the response can be replaced with the cross section, because the cross section is maximum only at certain values of projectile energy, okay? So the response is replaced with cross section, and the oscillator strength is nothing but the product of the partial widths of formation and decay width, and the eigen frequency is replaced with E projectile energy, E resonance, at which the Q value plus E resonance coincides with one of the excited states, and this is the incident energy, and this is the total partial width, which is equivalent to the damped factor of the damped oscillator, okay? Now, whatever width, whatever the energy state we are considering, it has certain lifetime, and it has certain energy width also. That will decide the excited state, and using Heisenberg uncertainty principle, like E into T is equal to H bar, here the corresponding value for energy is nothing but total partial width, okay, which is sum of gamma A and gamma B. This is equal to gamma A plus gamma B, okay. This is the lifetime, and the product of these two is given by H bar. By taking this, one can write down the final expression for cross section of a resonant reaction. This is given by pi lambda bar square. If you take separately, this is the maximum cross section of geometrical cross section, which can provide an idea about the maximum cross section a nuclear reaction can attain, and this is the statistical factor. This is the identical term involving the identicalness, and then this is the term which takes into account the dampedness in the system. So the kind of restoring force present in the damped oscillator, same thing we can imagine in the case of resonant reactions. This is called as the famous Breed-Wigner formula. So with this, let me close today's lecture. To summarize, I have provided the difference between resonant reaction and non-resonant reactions, and step by step I am trying to come up with an expression for the cross section of a resonant nuclear reaction. So in the next lecture, I will continue the discussion on resonant reaction, and also I will also discuss neutron induced non-resonant reactions, because in the previous lecture I have discussed non-resonant reactions induced by charged particles. We also should discuss the induced by neutrons also. Alright, I hope you have enjoyed today's lecture. See you soon. Thank you very much.